Hello, good morning. So I think the session began for the presentation. So my name is Jamal Rafique, and I did Ph.D. at Federal University of Santa Catarina under the supervision of Professor Antonio Braga, at Florianópolis. Currently, I'm a visiting professor at Federal University of Mato Grosso do Sul, Institute of Chemistry. So the title of my today's talk is Recent Advances in the Iodine Catalyzed Organic Transformations. Just for the convenience, I will subdivide this presentation into introduction, which I will discuss very briefly about the history or the importance of the cross-coupling reaction or iodine catalyzed transformations. Secondly, the most important focus of my presentation will be iodine catalyzed organic transformation via heteroatom iodine intermediates. So where I will highlight the formation of iodine bonding with carbon, nitrogen, phosphorus, oxygen, or other element in situ, which leads to the product. In the second part of the presentation, I will focus on the lab-sealing activities from Florianópolis in that particular area. And lastly, the conclusion. So I will begin my introduction with the oxidative coupling reaction. So, in organic synthesis, that is one of the wonderful or how to say well-known tool to access diverse range of compounds, diverse class of compounds. So generally we use that approach for construction of carbon heteroatom bond via CH bond functionalization or activation. Generally it's involved the reaction between nucleophile electrophiles, although there are reactions which follows the radical pathway. In the cross-coupling reaction, transition metal catalyzed cross-coupling reactions are emerged as a sustainable tool in last one decade. But still, there's a problem regarding the trans-metal contamination. So in order to eliminate this problem, we have some other approaches. We can use some non-metal catalysts, make the process more greener. So the second part of this introduction, which is about the iodine. So I will go into a bit history of the iodine. So iodine, which is itself known because of its properties since 3000 years BC, but its discovery happened in 1800 century, 1811. Iodine, from the beginnings of its discovery, are known to be highly soluble in organic solvent, and it has very poor solubility in aqueous or water. While from the beginning, scientists are trying to use it in organic transformation, and one of the reported or one of the known reported literature which is available is by Cersuschem for the reaction of iodine with the methyl ketones. And we know this reaction nowadays is haloform reactions. Now, the property of iodine itself, it's chemically a very weak oxidant. It's a weak electrophile, so it serves as a Lewis acid also. But beside this, iodine itself work or have the properties of electrophile or nucleophile, so it's worked as a dual activator in organic reactions. Now, iodine and iron, like in the form of salt, potassium iodide, sodium iodide, ammonium iodide, like these kind of salts, they can be easily oxidized by peroxides, oxidant to molecular iodine or to corresponding oxyoacids. Beside the diatomic form, I2, is with the very lowest homolytic dissociation energy. So it can be used as a source of radical species. Furthermore, due to lower electronegativity in the halogen formulae, it's easily form iodine cations. We form it or scientists generated in situ. Now, that's something which give liberty. So as electrophilic species, we can use it in various kind of transformation, though they are negative charge halogen family, but depending on the reaction condition, we can form the iodine plus in the reaction medium. So just give you a very historic background. So iodine is known in the literature for iodolactonization. So where we can take a substrate with a double bond and acid moiety, which can form a lactone with iodine linkage. Also, it can give us access to the iodocyclization with the product in the form of iodine. Now, this kind of thing is very important. If we are looking at the structure in the products, we are having iodines. So this gives us a very strong liberty for post-functionalization or post-modification of these compounds. We can eliminate them to get access to a double bond. We can make substitution reaction of this kind of substrates. Furthermore, iodine catalyzed reactions are also not new. So if we go into literature, and we will find one of the first report is by the Hebert in 1915, where they use a very low catalytic loading of molecular iodine for the dehydration of diketone alcohol to mesotyl oxides. So based on this information, we can have some comparison between iodine and transition metal catalysis. So generally, if we are comparing, so the reaction of iodines are mild, they are greater atom economic, they are more greener. Substrates results in a broad scope. Also, because of high availability of iodine or its salts, they are low cost and really stable, easily available. They tolerate the moisture or air atmosphere. Also, there is no need to dry the reaction involving the iodine. Furthermore, because of high catalytic activity in dilute and highly concentrated condition, we can perform the reaction under solvent-free condition. That's something makes the system completely greener. So, knowing that iodine itself has diverse applications, we can use as a catalyst. So, generally in organic synthesis, we can use iodine catalyst for coupling between two components via cross-coupling reaction or oxidative coupling reactions, where X can be any atom, any heteroatom, or beside carbon, can be nitrogen, oxygen, sulfur, selenium, phosphorus, tellurium, anything. So based on the type of reaction, generally there are two major divisions regarding the iodine catalyzed transformation. So the one is radical-based oxidative coupling, which I'm demonstrating in this slide. Now, generally, the radical-initiated coupling, in which iodine mediates decomposition of tertiary butyl alcohol to the hydroxide or tertiary butyl butoxide radical, and hydroxide ion through the single electron transfer. In the next, the tertiary butyl oxide radical extract a proton from the appropriate substrate to generate the stabilized radical A and tertiary butanol. In the third step of the reaction, the intermediate A formed is being oxidized by the iodine to form the cation species B. Now, the cation species B in the presence of a nucleophile result in the product. So this kind of approach is generally applied to the carbonyl compounds. A second class of reactions of iodine catalysis involve in situ iodination, which is proceeded by oxidative coupling. So the focus of my talk in this presentation will be on the second type. So this I will enter into the second part of my presentation, which is iodine catalyzed organic transformation via heteroatoms iodine intermediates. So in this case, I'm going to divide the presentation into various elements. For example, carbon iodine bond formation, nitrogen iodine bond formation, chalcogen iodine bond formation, phosphorus bond formation, iodine bond formation, etc. So In this approach, like I mentioned previously also, normally this C-iodine bond formation happen mostly with the carbonyl containing compound. So the CH bond functionalization of carbonyl group at alpha position result in the formation of iodo products, which can be post-functionalized into various organic transformations. So I took some recent literature on that aspect, which highlight the importance of this kind of approach. So in 2012, Wang and Zhang reported tertiary hydrogen peroxide iodine as a catalyst promoted oxidative coupling of acetophenones with amines at room temperatures under metal solvent-free conditions for the synthesis of alpha-ketamides. Now, the reaction which they propose, the mechanism for this transformation, involve initially the acetophenone react with the secondary amine. In this case, is the piperidine to afford the enamine 1. Now, this enamine 1 react with the iodine plus species, which is formed from the reaction of molecular iodine and the oxidant tertiary hydrogen peroxide, forming the 3-member iodinium cation. This iodinium cation on the cleavage result in the cationic iminium species 3, which with the subsequent loss of water in the presence of water, forming the alpha iodo acetophenones. This alpha iodo acetophenones is been substituted, the iodine is substituted in the presence of pyrimidines to form the intermediate with the piperidine moiety. Now, piperidine in the presence of tertiary butyl peroxide radical, forming the peroxy species, peroxy tertiary butyl oxide species 4, which with the elimination of tertiary butyl in the presence of tertiary butyl peroxide, forming the desired product. The second literature which I took on this topic is by the Pan co-worker, where they mentioned the iodine catalyzed synthesis of N,N-diaryl orthophenylene diamines from the cyclohexanones and anilines using DMSO and oxygen as oxidant species. So in this transformation, what they propose by mechanism, the first step is similarly to the previous slide. The alpha iodination took place in the presence of catalytic amount of iodine and oxygen DMSO. In the second step, via the oxidation of Kornblum, we get access to the diketo group B, is there is an excess of amine group. So instead of the second step, the reaction follow by the first step, forming the enamine species C. Now, the enamine species C in the presence of another equivalent of anilines, forming the oxime species D, which again, in the presence of molecular iodine and DMSO, lead us to the species E. Species in the presence of hydroiodic acid, which is one of the byproduct or one of the intermediate forming this reaction, lead us to the species F, which aromatize back to the desired product. The third article on that topic is by the Yutpan and co-workers, where they use the indoles and the N-heteroalide compounds, 5-member N-heteroalide compounds, for the C2 position carbon-nitrogen bond formation. So the mechanism which they proposed for this transformation was that molecular iodine under the reaction medium, or as we already mentioned, in the presence of tetrabutyl hydrogen peroxide, found the I plus species, which is a electrophilic iodine species. Then the nucleophilic attack of I plus species by the double bond of iodine at C2, C3 position, forming the iodinium anion-A, which on cleavage result to the resulting form of species B. This intermediate can be trapped by the nucleophilic azoles, resulting in the species C. Now, the species C, with the substitution elimination of HI, forming the desired product, and the formed HI in the presence of the oxygen tetrabutyl hydrogen peroxide, result back into the catalyst, which enter into the catalytic cycle. Another article on the same topic is by the Wu and co-workers with the title Iodine Catalyzed Oxidative Coupling to Construct Carbon-Oxygen Bonds for the Synthesis of 2,3-dihydroxyphines. So, where they are using adiramines or pyrazolone nucleus and acetophenones to get access to this class of heterocycles. Though the reaction is a bit complex, but if we check the beginning route, we can build up the mechanism. So the mechanism which they propose is the beginning of the acetophenones. As I already mentioned in the previous slides, they demonstrate that in the presence of molecular iodine in D-meso, it leads to the alpha-iodoacetophenone species. Now, that alpha-iodoacetophenone species in the presence of D-meso forming the glycosols. The glycosol in the presence of the triplic acid forming the protonated glycosol species which activate the aldehyde part. Now, this species in the presence of the pyrazolone nucleus result into the intermediate A, which underwent into the dehydration, resulting the alpha-beta unsaturated ketone species B. Now, that's the substrate via Michael addition to another substrate of pyrrolizine result into the intermediate 4A. Now, 4A by two different routes. One in the presence of iodine, the same approach we are observing here. Iodination took place. It happened with a terminal methyl and subsequently oxidation result in the product, or with the oxygen iodine bond formation in a path B, which lead us to the product also. Okay. Another work on the same topic is by the Yang and collaborators, where they use iodine as a catalyst for the functionalization of the azarenes like isoquinolines with the benzylic methyl groups, or with this methyl group of the toluenes via N-alkylation amidation cascade reaction. So in the second step of reaction, they perform the cyclization to get access to the iso-indolve isoquinolinones nucleus. So the mechanism of this transformation is, as I already mentioned in the previous slide, so it's begin with the reaction of iodine and the oxygen forming the I plus species. Now, this I plus species, which they mention, is result in the formation of the benzyl iodide via homolytic cleavage. So it follows by the radical pathway. Now, that benzyl iodide in the presence of the isoquinoline moieties forming the quaternary ammonium salt species A, which in the presence of tetrabutyl hydrogen peroxide forms the hemiaminal type peroxide species, which undergoes the oxygen-oxygen bond cleavage, forming the one of the product of this transformation. Now, the intermediate form in this transformation was the HI, which oxidized back to the molecular iodine, which re-enter in the catalytic cycle. The last article and that topic which I selected is by the Hanu group, where they used the stearyl bromides and potassium cyanide to prepare the cyanide derived of the stearyl bromides, or the same intermediate can lead into the cyclization and to get access into the benzosylenophene moieties. So the mechanism what they propose was with the beginning of iodine reacting with the double bond of the stearyl bromide, forming the iodinium cations. This three-member ring is being attacked by the cyanide, resulting into the intermediate B. Now, intermediate B, depending on the reaction condition, for example, if it's like a short reaction type and 100 degrees centigrade, results into the cyanide intermediate. While for a longer reaction time, at 110 degrees centigrade, a homolytic cleavage happens between selenium and cyanide moiety, forming the selenium radical species, which cyclize to species C, and with the loss of proton, lead to the benzosylenophines. The HI form in this reaction, like I minus form in this reactions, regenerate the catalyst. Okay, with this I will move into the second part of this talk, where I will talk about the nitrogen iodine bond formation as intermediate to lead into the product. The article which I selected for this topic is by the Wang and collaborators, with the title that iodine catalyzed diamination of styrene in water with oxidation of hydrogen peroxide. So they use the TMDAI, which is trimethyl dodecane ammonium iodide species, as a catalyst to get access into the dihydroindole moieties. So the mechanism which they propose for this transformation begins with the formation of Eomannus species, which in the presence of the styrenes, the two aminostyrenes, result into nitrogen iodine bond formed intermediates. Now, that intermediate loses the I- species, which oxidize back and re-enter in the catalytic cycle, generate the species B. Now, the species B's lead to the cyclization of intermediate C. Now, this intermediate, in the presence of amines, anilines, result in the formation of the final product. The second article in this topic, which I select, is with the title Hypoiodate Mediated Synthesis of Isoxazolone from Aldoxamines and Alkenes using catalytic potassium iodide and oxone as a terminal oxidant. For this transformation, the author used aldoxamines and styrenes to get access into the isoxazolines nucleus. So the transformation began from the reaction of potassium iodide and oxone to form the active species of this catalytic transformation with I minus, I plus, which reacts with the intermediate 2, the double bond intermediate 2, forming the iodinium three-member ring. Now, this iodinium three-member ring is being attacked by the double bonded styrenes compound, lead to the intermediate 8, which on subsequent cyclization forming the tetraoxazoles nucleus, which under reaction condition leading to the oxidation. Okay, with this I will enter into the another part of this talk, which is the formation of sulfur iodine bond intermediate, which leads into the final products. So the work which I selected, the first work I selected for this transformation is from the Pagniti and collaborators, where they use different kind of arenes in the presence of thiol to prepare diverse classes of sulfonylated products. The mechanism they proposed for this transformation initially began from the thiol oxidized to the disulfides in the presence of iodine, which react with iodine again, forming the electrophilic species of sulfur, which is A. Now, species A is being attacked by the activated ions at carbon 1 position, lead into the intermediate species B. This species B, with the loss of HI, forming the desired product. Now, the HI in the presence of DMSO, which is oxidant for this transformation, results in the iodinated hydroxy species, which with the elimination of water dimethyl sulfide, recovering the catalyst, which re-enter in the catalytic cycle. Another article in this topic is with the title Iodine Catalyzed Cascade Annulation of Alkynes with Sodium Aryl Sulfinates. So the assembly of 3-sulfenylcumulines and 3-sulfenylphenolene derivatives. So in this work, Zheng and collaborators used the alkynes and sodium sulfinates to result into the cyclized product and sulfination of these products. So the reaction begins from the reaction from the formation of active species, electrophilic species of sulfur, which is organosulfur iodide. Now, this electrophilic sulfur species is being attacked by the alkynes, which by cascade reaction forming the cyclized intermediate C, which leads to the product. By eliminating the HI, now HI in the presence of the oxidant DMSO oxidized back to the molecular iodine, which in the catalytic cycle. Another article which I selected, which is published very recently in the Green Chemistry by the Ishikawa group, where they use flamine iodine coupled organocatalysis for the aerobic oxidative direct sulfonylation of indoles with thiols under mild conditions. So in that work, what they demonstrate actually is the formation of the lead reactive intermediate or species, which is electrophilic sulfur species, which react with the indole at C3 position, forming the product and resulting in the I minus and H plus, which form the HI. Now, the flamine job is also as a co-catalyst, which oxidizes the iodine in this transformation back to molecular iodine. Okay, with this I will enter into the another part of this presentation, which is the phosphorus iodine bond formation to lead into the desired product. So the article which I selected for this topic is by the Prabhu, where they use different types of phosphites and nucleophile, which they use amine, alcohol, and sulfoxamines in the present molecular iodine as catalyst to phosphorylate amines and alcohols. So the catalytic transformation for this reaction involves or the beginning from the molecular iodine to the I plus species. Now, this I plus species is being attacked by the phosphites, lone pair of electron, forming the iodophosphide intermediate, which is attacked by the nucleophile, leading to the desired product and generating the imine species, which oxidize back to the catalyst in the presence of the oxidant. So with this, I will enter in the second part of my presentation, which is the iodine catalyzed chalcogenation reaction. So mostly I will mention results from the lab setting in Florianopolis, because we are using this approach in some of our lab activities. So we are using iodine catalyzed chalcogenation reactions to access different kind of organic moieties. Now, one of the most important methodology to introduce chalcogen atom in an organic molecule is by the use of chalcogen electrophiles. So, by forming the chalcogen electrophile, we can functionalize different kind of organic moieties. For this purpose, there are many type of electrophilic chalcogen, like many species exist. Counter anion exists in literature, so which variate from the tosalite species to the phthalamides to the halides. So there is a diverse class of electrophilic chalcogen species. Now, with relation to that presentation which I'm doing today, with iodine. So iodine has some liberty, because critical amount of iodine under mild oxidant, for example, DMSO, and half molar equivalent of the dichalcogenate result in the formation of like electrophilic species. We can generate this electrophilic species in situ and react with the two equivalent of any of the substrate, so which lead us to the biologically relevant sulfur selenium tellurium containing compound via CsP2 bond chalcogenation or active functionalization. So the first article which I'm going to present is with the title of regioselective solvent metal-free chalcogenation of imidazopyridines by employing iodine DMSO as a catalytic oxidant system. So in that work, we use different kind of imidazopyridines, dichalcogenate, sulfur selenium, and molecular iodine as a 5 mole % catalyst by using 3 molar equivalent of DMSO. So the reaction was being performed without the need of high amount of DMSO as a solvent. So I will say the reaction was solvent free, which lead us a regioselective product at C3 position, the chalcogenated products. Now, why we were motivated to go for this transformation? Because there are several drugs commercially available. Many of them are in Brazil also, which has imidazopyridine core. For example, alapidine, zolimitin for sedative purposes. We have nicobidine, saridipine for anxiolytic purposes. While also there are some for the peptic treatment, peptic ulcer treatments. Besides this one, recently we published via collaboration a work where we demonstrated that these hybrid compounds with the imidazoheterocycles and organoselenium moiety result into very excellent hybridization. So we got some good results where at very low concentration with very low toxicity, this compound was showing promising anti-cancer properties. So with this, we performed several optimization reaction. What we found that 5 mole % of iodine, 3 molar equivalent of the DMSO at 90 degrees centigrade for 9 hours was best condition to lead into the self-selenilated products. So after confirming the optimized condition, we applied the scope by variation of diselenides, which work perfectly. Even the reaction goes smoothly for the aliphatic diselenides. We also extended the scope to the different organodisulfides moieties, where the reaction also works smoothly. The reaction scope was also being extended for the imidazoheterocycles. So while keeping the diphenyl diselenide or diphenyl disulfide moiety constant, we performed the variation of substitution of imidazoheterocore, where the reaction also resulted the product in good to excellent yield. In one of the experiments where we are using the C2 unsubstituted imidazocore, the Chalcogenation was taking place at C3 position, which highlight the reduced selectivity of this reaction. Also, we use the imidazopyrimidine core also for this transformation. One of the biggest problem in organic methodologies or new synthesis development is the scale of the reaction. So the reaction generally work perfectly at a minor scale, while the scale of reaction is not very effective. For pharmaceutical or for industrial purposes, that can be a big problem. So with this motivation, we normally perform scale-up reaction just to check whether our reaction is applicable on higher scale or not. So we applied this transformation at a higher scale, like a 20 folds higher scale, where the reaction resulted the desired product without any substantial decrease in the yield, which signify that this can be a practical route to access this kind of selenitrated sulfinated products. After this, we performed several control experiments to propose a mechanism, which began a reaction in the presence of tempo, 4 to 5 equivalent of tempo as a radical inhibitor, where there was no radical inhibition, signifying that radical species could not be involved with this transformation. Replacing the diselenide with phenylselenium bromide as an electrophilic selenium species in the absence of iodine as a catalyst, the reaction leading to the desired product in 25% yield, which point out that selenium is working as an electrophilic species. In the next step, we performed a reaction in the presence of Hi as a catalyst instead of molecular iodine, which results the product in 79% yield also, which signify that Hi could be the intermediate in this transformation. Now, if Hi is the intermediate in this reaction, why not to inhibit? Why not to capture that at Hi? So with this intention, we perform the standard reaction in the presence of base. So we use like a DAPCO, Haven's base, and triethylamine to capture if there is any acid species formation. Interestingly, when the reaction was performed, there was a great amount of quenching in the reaction. So the base is quenching the reaction. So this reaction highlight that Hi could be the species as we tried in a previous reaction. So based on this one, we perform some other reaction, try to capture something in this transformation. So with GCMS or LCMS, we were unable to capture any of the derivatives, but with NMR, we were able to capture one of the byproduct forming in this reaction, which is the dimethyl sulfide. So based on these experiments and some literature, we proposed a mechanism for this transformation, which began from the reaction of molecular iodine with dichalcogenate diselenide, forming the electrophilic species A, which is being attacked by the heteroarenes, in this case imidazopyridines, forming the species B. Species B, with the release of Hi forming the product. Now, this Hi in the presence of dimethyl sulfoxide is oxidant, forming the protonated species, which in the presence of another Hi leads into the dihydroxy iodidated dimethyl sulfide species, which with the release of water forming the species D. Now the species D in the presence of iodide anion forming the catalyst, which enter in catalytic cycle, and dimethyl sulfide, which we captured during this reaction. The next article in the same topic is with the title Iodine, DMSO iodine catalyzed oxidative C-selenium C-sulfur bond formation. A reduced electrosynthesis of unsymmetrical chalcogenides with nitrogen or oxygen containing arenes. So we use different kind of activated arenes, beginning from anilines, anisols, and phenolic compounds, and dialgonic chalcogenate, or even thiols. So we get motivated for this transformation because this kind of very simple compound has known pharmaceutical properties, biological activities. For example, like this kind of sulfides, selenides, are known for the antitubulin cytotoxic activity or lipoxygenase inhibitors. Recently, we also demonstrated that these compounds also demonstrate anti-Alzheimer properties. So with this motivation intention, we perform some optimization reaction, and for this, reaction, what we found that microwave irradiation was working perfectly. So we use 20 mole percent of molecular iodine as a catalyst, 3 molar equivalent of the DMSO with 100 watts microwave potential, 110 degrees centigrade for 10 minutes, resulted into desired product by using only half molar equivalent of the dichalcogenide, dicyanide species. So after optimizing this reaction, we extended the scope of this reaction by variation of the amines, also by the anisols or phenols, which result the product reaches selectivity. So depending on the orientation, if para position is being blocked, the product was getting at ortho position. Next, we also performed the scope of this reaction by using different kind of substituted diaryl diselenides as well as aliphatic diselenides, which is the desired product in good to excellent yields. We extended the scope of this reaction to the disulfides also, which result in a product in good to very excellent yields. We also performed a control experiment, but in order to save time for my presentation, I'm skipping it. So the mechanism which we propose for this transformation is similar to our previous reactions, which began with the formation of electrophilic chalcogenide intermediates or species. Now, this is being attacked by the activated arenes depending on the position, forming the species B, which results in the product and subsequent release of 2 equivalent of HI. Now, from HI, in the presence of DMSO as a mild oxidant, we recover back the molecular iodine. With this approach, we also applied the same transformation to the bicyclic arenes, and the reaction worked perfectly, reached selectivity at at C1 position. So the chalcogenation happened at the carbon 1 position to lead into these kind of products. Another article which I will mention on that topic is with the title Synthesis of Unsymmetrical Diorganyl Chalcogenides Under Greener Conditions. So the use of molecular iodine DMSO system under solvent metal free conditions. So we were using the different kind of diagonal dichalcogenide, including selenium, tellurium, sulfur, aryl boronic acid under microwave radiation, lead into the unsymmetrical chalcogenides products. So after a series of optimization reaction, we observed that 10 mole percent of molecular iodine, 2 molar equivalent of DMSO as an oxidant under microwave radiation of 100 watt potential, 100 degrees centigrade, 10 minutes was sufficient to result the product in good yields. So after optimizing the reaction, at first we performed the scope of this study by the variation of the boronic acid moieties. We also extended the scope of this reaction by the variation of the organelle moieties of the ditellurides. With the very excellent result from the telluride, we extended this reaction to the selenides also, where the results was also from good to excellent yields. For the sulfides, there was a slight decrease in the yields, which could be explained according to the literature that due to the strong sulfur-sulfur linkage. The mechanism for this transformation is also the same. So we generate the electrophilic chalcogen species from the reaction of iodine and dichalcogenide, which in the presence of boronic acid from the species A. Now, the species A release iodide anion, which is being attacked again by the B, read into the product, while HI, now the HI is being oxidized back to the molecular iodine in the presence of DMSO. Very recently, we also tried to change this catalytic system to another salts, or to the salts, for example, ammonium iodide. What we find that 10 mole percent of ammonium iodide in a mixture of DMSO water, like 50%, 1 molar equivalent of acetic acid, 110 degrees centigrade, and 6 to 14 hour reaction time, we can access regioselectively our hetero-arenes substituted chalcogenative products. So at first we perform the optimization reaction, which I already mentioned in the previous slide. So after optimizing the reaction, we applied the scope to the different disulfides. We also performed the scope to the different imidazopyridines. We extended the same transformation to the other heteroarenes also. For example, indole to the indazolines, indazoles, thiazolimidazoles, imidazopyrimidines, where the reaction was smoothly not only for the sulfur but the selenium also. The mechanism for this transformation began of the reaction of ammonium iodide in the acidic medium, forming the HI. Now, this HI in the presence of a dimethol, forming the active component of this catalytic transformation is a molecular iodine. Now, molecular iodine in the presence of the dichalcogenide, forming the electrophilic chalcogen species, which leads into the product via the intermediate 15 and regeneration of the HI, which will enter in the catalytic cycle. With this, I will conclude my presentation. In recent years, iodine catalyzed organic transformation are evolved as a versatile tool to access not only carbon-carbon, but carbon heteroatom bond formation. These reactions are generally energy efficient and are eco-friendly. So in the first class presentation, which I already highlighted, on the formation of intermediates, carbon, nitrogen, sulfur, phosphorus, iodine, which lead into the different products. In the second part of my talk was the lab serine activities. So among different kind of transformation we are performing in lab serine. So one type of transformation in the lab serine, we utilizes the molecular iodine or iodine species, and we demonstrate them as an efficient catalyst to access the chalcogen heteroaryl moieties compounds. For example, indole, imidazopyridines, chromones, coumarines. The liberty of this transformation that we need only the half molar equivalent of the diorganyl dichalcogenides. And these reactions with the heteroaryls normally work via CsP2 bond functionalization or by using boronic acid. So some of the key features for this transformation are they all are catalytic. Mostly we perform the reaction under solvent and metal-free conditions. The reaction are at economic. The reaction are with a very broad scope. The reaction are easily scalable at a gram scale. The reaction don't need any pre-treatment or need a dry atmosphere or organ atmosphere. And also we avoid the pre-formation of the electrophilic species in the reaction. So we can generate them in situ and use them in situ for our product. Okay, with this I will acknowledge different groups which funded the project. Particularly, I will highlight the contribution of the GSK and the Cersuschem in realizing different projects we conduct in the lab in Florianopolis. And also, I'll acknowledge all the people involved in this project, particularly my ex-advisor, Professor Antonius Braga. Thank you very much for your kind attention. Any question? Ellen is asking a question that this reaction, like electrophilic aromatic substitution reaction, doesn't work with electron withdrawing group or for the low yields. Generally, when we try to reaction with the electron withdrawing group, for example, like nitro or fluorocompounds, the reaction was totally inactive. So we were unable to get any product. So for this reaction, we need arenes to be activated. Because if you check the mechanisms, there is generally an electrophilic, nucleophilic attack of the arenes to the electrophilic species of the chalcogen. Okay, seems there is no more questions, so we can leave. In case anyone has any question or want to ask later, you guys can send me email at any time, no problem. Okay, thank you all. And hope to see you during the workshop which is going to be begin from 1st October at São Pedro, I think. So best of luck. See you all during the event. Bye.